Have you ever wondered how hot the sun is? It's a question that has intrigued us for centuries. The sun, our closest star, is the life-giving powerhouse of our solar system. Without it, life as we know it wouldn't exist. But what makes the sun so hot? The sun's heat is a mystery that scientists have been unraveling for decades. It's not as simple as you might think. You see, the sun isn't just a big ball of fire. It's a gigantic glowing sphere of hot plasma, composed mostly of hydrogen and helium. Its heat doesn't spread out evenly, but rather it varies from the core to its surface. Let's start from the inside out. At the sun's core, the temperature reaches a staggering 15 million degrees Celsius. That's hot enough to sustain a process known as nuclear fusion, where hydrogen atoms collide and fuse together to form helium. This process releases an enormous amount of energy, which heats up the core. Moving outwards, we come to the radiative zone. Here, the temperature drops to about 2 to 7 million degrees. Energy from the core travels slowly through this zone, taking up to 1 million years to reach the next layer, the convective zone. In the convective zone, the sun's plasma rises and falls like boiling soup, carrying heat towards the surface. The temperature here cools down further to about 2 million degrees. Finally, we reach the sun's surface, or the photosphere, where the temperature is a relatively chilly 5,500 degrees. This is the part of the sun we can see from Earth, glowing brightly in our sky. So, as we've seen, the sun's heat is far from uniform. It varies from the scorching core to the cooler surface, all thanks to the processes of nuclear fusion and convection. So the sun isn't just a big ball of fire. There's a lot more to it. The core of the sun. Now that's where all the magic happens. Imagine a place over 15 million degrees Celsius, where the pressure is so intense it's 200 billion times that of Earth's atmosphere at sea level. This extreme environment is where the sun, like all stars, performs its most critical and fascinating act: nuclear fusion. Nuclear fusion is the process that powers the sun and produces its heat and light. It's also what makes the sun, well, the sun. But what exactly is going on in there? Let's break it down. Deep within the sun's core, hydrogen atoms are under such immense pressure that they overcome their natural repulsion for each other. Instead of bouncing off one another as they would in a less extreme environment, these atoms collide and fuse together. Each collision creates a helium atom. But here's the interesting part. A helium atom weighs slightly less than the 2 hydrogen atoms that created it. So, where did that missing mass go? The answer lies in Einstein's famous equation, E=mc², which tells us that energy, E, equals mass, m, times the speed of light, c². In the sun's core, the missing mass is converted into energy, and not just a little bit of energy. We're talking about a tremendous amount of energy. Every second, the sun converts about 600 million tons of hydrogen into helium. This process releases an amount of energy equivalent to billions of nuclear bombs. This energy moves outward from the core, eventually reaching the sun's surface and radiating into space as heat and light. That's the light and warmth we feel here on Earth, 93 million miles away. So, the sun's core is a powerhouse, converting mass into energy through nuclear fusion. This incredible process is what makes the sun shine and gives it its heat. It's where all the energy that drives life on our planet originates. And to think it all happens in the heart of our nearest star. But how does the heat from the sun's core reach us here on Earth? Well, it's quite a journey, that's for sure. Picture a photon, a tiny particle of light born in the immense pressure and heat of the sun's core. This photon, a byproduct of nuclear fusion, is the bearer of the sun's energy, destined to embark on a grand tour to the surface. The first leg of this journey takes our photon through the radiative zone. This is a region where the energy travels by radiation. That is, the photons are absorbed and re-emitted in all directions by the sun's dense plasma. But wait, this isn't a straightforward sprint. No, it's more akin to a chaotic dance. The photon is absorbed, then re-emitted, absorbed, then re-emitted, and so on. This process repeats countless times, causing the photon to zigzag its way through the radiative zone. Then, we arrive at the convective zone. Here, the sun's plasma isn't dense enough to absorb the photon and a different process takes over: convection. You can think of convection like a pot of boiling water. The hot water rises to the surface, cools down, and then sinks back down to be heated once again. Similarly, in the sun's convective zone, hot plasma rises towards the surface, cools down, and sinks back towards the radiative zone. Our photon hitches a ride on this convective current, finally making its way to the sun's surface. The journey, however, is not over yet. The photon must still travel the vast expanse of space to reach us here on Earth. Yet, the most time-consuming part is done. After potentially spending thousands to millions of years bouncing around within the sun, the photon is finally free to race through space at the speed of light, bringing us the warmth and light we experience every day. Thus, the energy created in the sun's core takes a long journey to reach the surface. And what about the sun's surface? How hot is it? Well, let's dive in. The surface of the sun, known as the photosphere, is the layer we can see from Earth. It's the part of the sun that shines bright and gives us our daylight. And it's hot, but not nearly as hot as the sun's core. The temperature of the photosphere is about 10,000 degrees Fahrenheit. Yes, you heard it right, 10,000 degrees. That's hotter than any oven or furnace we could ever dream of building on Earth. Now, the photosphere isn't just a simple, flat surface. It's a bubbling sea of plasma, constantly in motion. And within this turbulent layer, there are some fascinating features. One of these are sunspots. Sunspots are darker, cooler areas on the sun's surface. They're cooler, but don't be fooled. A cool sunspot is still hotter than anything you've experienced, with temperatures around 6,500 degrees Fahrenheit. Sunspots are the breeding grounds for another amazing solar phenomenon, solar flares. These are sudden, violent eruptions of energy that blast out from the sun's surface. Solar flares can release as much energy as 1 billion atomic bombs. And remember, this is all happening on the surface of the sun, the coolest part of the sun. So let's take a moment to appreciate the sheer power and energy of our sun. From its core, where temperatures reach millions of degrees, to its surface at a mere 10,000 degrees, the sun is a fiery furnace of nuclear reactions. It's a powerhouse of energy that lights up our sky, warms our planet, and supports all life on Earth. And even though it's 93 million miles away, the sun's surface is still hot enough to make life as we know it impossible anywhere closer. Imagine standing on a planet closer to the sun. Even the cool sunspots would be enough to vaporize you instantly. So, the surface of the sun, while cooler than the core, is still a scorching place. Now, how does the sun's heat affect Earth? Well, the sun's heat reaches our planet primarily through a process known as radiation. This is not the kind that makes you glow in the dark, mind you, but the kind that travels through space in the form of waves from the sun to the Earth. It's like an invisible energy delivery service that operates non-stop 24 hours a day, 7 days a week. This radiation arrives at Earth's atmosphere, where some of it is reflected back into space, but a good portion of it, about 70%, is absorbed by our planet. This absorbed energy heats the Earth and is responsible for our planet's temperature. Without it, we would be living on a frozen rock, not unlike the dark side of the moon. But it's not just about absorbing heat. The Earth also radiates heat back into space. It's this balance between the heat absorbed and heat radiated back into space that determines our planet's average temperature. Now, you might be wondering, what happens if this balance gets disturbed? Well, that's a great question. If Earth absorbs more heat than it radiates, the planet warms up. This is what's happening with global warming. Conversely, if Earth radiates more heat than it absorbs, the planet cools down. The sun's heat plays an integral role in Earth's climate and weather too. It's the driving force behind wind, rain, snow, and all other types of weather. The heat causes water from the oceans to evaporate, forming clouds, which can then lead to precipitation. It also creates temperature differences between various parts of the Earth, which in turn creates wind. So, the sun's heat does a lot more than just providing us with a nice warm day. It's the engine that powers the Earth's climate system, driving the winds, fueling the rain, and making life as we know it possible. So, the sun's heat not only makes life on Earth possible, but also shapes our climate and weather. Thanks for watching. Don't forget to like, comment, and follow.